Okay. Joseph is here. Nice. Wondering about you. So you may notice in the syllabus, we're actually going back to chapter 4, which we're already in once. I originally took the lead from what they do at OSU and OIT, and they do this, and I actually agree with that now that I've taught it a while. But in chapter 4, we had like 3 or 4 forces on a beam, and we basically turned them into one, and then we located where it was. Well, doing the same thing here. It's just that now we have infinitely many loads. So now we're talking about something that looks like this. And we've already talked about this, but in the real world, very seldom do you just have one force in one location or even 2. You usually have infinitely many of them. So for instance, and these are things that I've talked to you about a little bit before, in a house, in a residential environment, you calculate the floor load as 450 pounds per square foot. And that's thinking of it as just loaded with people. So it's like everywhere. There's forces everywhere. There's not just one force. The whole room is full, 50 pounds per square foot. The roof is 40 pounds per square foot. And again, that's live plus dead, and that's snow. And so again, where's the snow? Everywhere. It's not just one point. And so that how truss that you are working on, and hopefully check with me today, and you're giving it to me today, that's kind of what we did. We started out with a distributed load like this, and then we reduced it to just point loads as a result. And that's kind of what we do here. And so if this is a linear, let's see, is that the right word for this? Is it written down anywhere? This load would be given as something like this. Like this load might be considered to be, say, 120 pounds, but it's not 120 pounds, it's 120 pounds per foot in terms of units. And that's not necessarily obvious. So I want you to kind of think about that as we roll along here, but that's 120 pounds for every foot, not 120 pounds total. Notice it could be 120 pounds an inch. And so do you see why the length designation has to be there? It's not 120 pounds total. So it's every one of those arrows is 120 pounds, and they're a foot apart, if you will. That's kind of the idea. Now, if I divide it by 12, does it make sense? You could say that that's 10 pounds an inch. Wouldn't that be the same thing? And that's kind of the idea here. Is there's literally infinitely many sort of arrows now. Instead of, I won't say forces, but I mean the same thing. That's what distributed means. Infinitely many arrows. And so we're thinking of this as really just an arrow every foot. 120 pound arrow every single foot. And that's true, but that is the same as 10 pounds an inch. And we could even go down from there. There's literally infinitely many. Now in this particular beam, because those are even, like it doesn't change, it's just 120 all the way across. And by the way, that's super common for that to be the case. You're going to have an even amount of snow sitting on the roof. You're going to have an even number and an even amount of people. So let's say that this was, say, 14 feet long. It actually is super easy to turn that into just one force instead of infinitely many, because you remember we're doing the sum of the moments and all that, and we had to consider every arrow. Well, if there's a million of them, how are we gonna do this? Well, because that's 120 pounds per foot, and we now know that there are 14 feet. Notice the units, pounds per foot times 14 feet. Obviously, those units would cancel. So whatever 120 times 14 is, turns out to be 1680. So that's just one force now. Does that make sense? Like I can just make one arrow for that. There's 180 pounds sitting on that, or 1,680 pounds sitting on that beam. But the question is, where is it? Where do I put that arrow? Is it on the left side? Is it on the right? Is it in the middle? Where is it? Yeah. And this is something that you would have addressed in calculus. Certainly if you had me, because I like this engineering stuff, I taught you this. That's 1680 would be right there. So now instead of infinitely many, we have one. And this would be exactly at the center, 7 feet in. Doesn't look like a 7. This is sometimes called the centroid. You might see that in your assignment. But the better language for that is center of mass. You probably see center of mass more often. So that's awesome. We just took millions of forces, not just 10 or 12, and made them into one. So cool. That's the center of mass. That's where it acts. And I'll erase this, but then the idea would be is if that actually is a beam, and so it's sitting on a wall over here and a wall over here, then of course, half of it, because everything is symmetrical, like we saw with our truss, for instance, that means half of it, one post would support half of that, 840, the other post would support 840. Actually, I don't really think I need to erase that. I think I could add that on here. So does it make sense now? If that was sitting on a couple of posts, that would now be, well, we'd say an equilibrium. Notice there's no forces trying to get it to go left and right, so it isn't moving left and right. And as long as those posts are able to support 840 each, then there's no vertical motion, and so life is good. Now, next term, we're going to look at strength of materials. You might see the word rigid in your book. It'll say that's a rigid beam. And what they mean by that is it's not bending at all, which is a lie. It is bending. It's bending before you had any weight on it. It bends under its own weight. But strength of materials is, well, you know, what beam do you put there? Because obviously it's going to want to bend down, and you can appreciate if you put a piece of balsa wood there, it's gone. Like 1,680 pounds on one of those balsa wood, it's gone. So, you know, we have to know how the beam's going to behave. So, you know, will the beam actually support 1680? Sort of sitting in the middle of it, if you will. Well, certain beams will, certain beams won't. Certain sizes, certain materials, that's kind of what strength of materials is about. So assuming the beam can withstand that, assuming those posts don't ultimately, if we work our way down the building, assuming those aren't, you know, poking into the ground, you can probably appreciate if that was a pretty skinny post, like the size of a broom handle, and you just set it on the dirt, that's going down into the ground. So it's like, you got to snowshoe that. You got to put a footing underneath, a concrete footing underneath the house that acts like a snowshoe. And again, we've played with that a little bit in this class. And so, you know, there's no guarantee that that's actually going to stay stable. We still have stuff to do to make sure that happens, right? Choose the right beam and make sure there's a footing underneath the house supporting that. But this particular load is ultimately rectangular, and loads are not always rectangular. So let's switch gears and take a look at that. What if the load is triangular? In other words, it looks like this. I still have the same beam, but what if this arrow is this long and the other arrows, though, are not the same length? But it wouldn't necessarily be the center like the other one. Exactly. So it's still going to have a location, but it's not going to be in the middle now. And it would be extremely important for us to figure out where the heck that thing is. Do you understand that? Because I can't deal with infinitely many arrows and infinitely many forces. I've got to resolve this to one force. But the question is, where is it? Now, again, I could just tell you where it is and we could move on. But I want to spend a little time here and kind of show you. And also because calculus is kind of cool. Second thing I want to say really quickly is, like, why would this ever happen? Like, how could you get a triangular load? I mean, do you have like short people on one side of the room and tall people on the other? I mean, how would this ever happen? Is this just a theoretical construct? Like this never happens? And just out of curiosity, I'll tell you where it happens. If you have a foundation wall made out of concrete, because your intention is to have living space right here, but out here is dirt, and we've played with this a little bit in a few different examples, then you can appreciate all that dirt is kind of pushing on the wall and wants to tip it over. And so we had a project where we looked at basically what forces are there on the house pushing back against that force. What we didn't look at is what's the overturning moment. In other words, how hard is that dirt pushing on that to actually make that one to tip over? Again, that's a moment calculation. And we got to get that right. Like that's the other half of the calculation that we didn't do before. And that's because we didn't know what we're about to know today. Well, that's a triangular load because up here, there's not very much dirt. Whereas the deeper you go, the force gets larger and larger and larger. In other words, at the top, you only have a foot of dirt. And so that has a smaller force, but the deeper you go, the more force there is. Now, maybe that's not super obvious to you, but have you ever swam down really deep in a pool? There's more force at the bottom on you than there is at the top. I think I told you guys, I can't remember who I told this to, if it was you guys, but I tried, wasn't it you guys? I tried when I was a kid, like, I'm gonna go down there with the hose and just hang out and breathe. But it's like, I didn't have the strength to lift 8 feet of water, think of it as a column of 8 feet of water. Water weighs like 8.5 pounds a gallon. So that was like, what is that, 8 times 8, 64. It was like a 64-pound weight on my chest. So some of you guys work out, a couple 45s, 3 45s on your chest, you're not going to be able to breathe. That's what's happening when you're underwater. Well, if I'm only a foot deep, that doesn't weigh that much. It's 8 pounds. I can breathe there. But you go down, can't breathe. I mean, that's a triangular load. And so that's an extreme. Retaining walls are where you see triangular loads. Any theoretical questions about that? I'm not going to spend any more time on that right now. I'm just going to get after a triangular load, but retaining walls are huge when I'm constantly having to turn this kind of thing in to engineers, because I'm always designing houses on hills, and so this just happens all the time. So awesome. Anyway, triangular loads exist. What I just mentioned a second ago, notice is interesting. Water weighs 8 pounds a gallon. I was 8 feet deep. And so that means the biggest force down there at the bottom was 64 pounds. And then it would just get less and less as you moved up. Notice I had to calculate that. Your problems are going to be a little more sterile than that. Like you're going to be given just some magic number over here. Like let's say this is 240 pounds per foot. But notice I'm actually aiming at this tallest one, and that's not all of them. The previous one, it was all of them that were that tall, right? But this one's 240 over here. And of course, that would mean it's 0 over here, right? And you could probably get the middle. What do you think the middle is? 120, it'd be half of that. And so the problem is here, not only do we have infinitely many forces, but every single one of them is different. Does that make sense? So that seems like a problem. Notice the total is actually not that bad, like the total force or the total weight. Total force or weight, those are going to be kind of used interchangeably in this section. Force and weight mean the same thing. Well, a second ago, in a sense, this was a rectangular load. I didn't write that down at the time. Rectangular. This is a rectangular load. And so didn't we take 120 times 14, kind of thinking of it, if you will, of this as a rectangle? Well, down here we got a triangle. Well, you know, to find the area of a triangle, if you take the area of that thing, again, let's just keep this at, let's go a different length. Let's say this is 18 feet this time. So if you take 240 times 18, hopefully you can appreciate, well, that looks just the same as we did a minute ago, right? Like that was for a rectangular load. Well, what do we do for the area of a triangle? We don't take height times length and we're done. What do we do? Half of that, right? So my machine says 240 times 18 times a half is 2160. So last time we got 1860 for the total force, and or 1680, and we said, sweet, 1,680 pounds, that's right here in the middle. So we now know our force is 2160, but we don't know where to put it. You see what I'm saying? Can you appreciate that since there's more big arrows on the right than there are on the left, that it would be like pushed to the right? It's not going to be in the middle. It's going to be over here somewhere. Doesn't it sort of feel like it, it's probably like right in there somewhere. So, where is it? And again, the cool thing about math is it's not in some random location. Like it's a nice clean fraction, as it turns out. Really nice fraction. Like you might guess, well, maybe it's 3/4 of the way over. Like if I cut this in half, like we did here, and then cut it in half again, maybe it's right there at 3/4, or maybe it's like 3/5, or maybe it's 2/3 of the way over. You see what I'm saying? And it actually turns out to be quite that nice. It isn't like 97/185 or some weird number. It isn't like the square root of 2 or some crazy number. It's actually a nice clean fraction. But we actually got some work to do to kind of figure out how that works. And I want to kind of show you something cool here. So the issue then is basically now, where the heck is the center of mass? Where do I put this? So let's pause for a second and let me show you kind of a neat calculation here. Teach you something. So pause. And this is something I taught in calculus, which, that was a year ago at best. And so you don't remember it, right? Even if you were there and understood it, you still don't remember it. So I just want to show you something kind of logical really quick. So let's say we got not millions of forces, but just 2. And I'll put one of them here. And I'm going to call this weight instead of force. I could say force, I could say weight, but you're going to see weight a lot in some of the book problems, and that's fine. It means the same thing. Weight is pounds, force is pounds, right? So there's weight 1, and here's weight 2. And notice those are different weights, and there's only 2. There's not millions, there's just 2. And so do you agree that if those aren't the same, then the center of mass is not going to be in the middle? And so haven't we been doing moment calculations to figure out kind of where all that goes down? And so that's exactly right. That's exactly what we're going to do. But I'm going to do some kind of interesting here, which is, and you should understand, I can take the moment around any point I want. To keep it really general, though, I'm actually going to go out here and find the moment around a point that isn't even in the picture, which is kind of cool to think about, that could be the case. And since that's weight 1, I'm going to say this distance right here is x1, like that's how far that is away. And then that means that other one would be x2. That's how far away. And I don't really know where the center of mass is, so I'm just going to kind of stick it in here somewhere. And the symbol for center of mass is x bar. And so that's what I'm after. So this is the center of mass. So I'm after, where is that? Like, what do I do to those 2 forces to figure that out? Well, remember, the center of mass is the balancing point. So I could kind of set sort of weight 1 times this distance, and then weight 2 times this distance, and set them equal to each other. Or I could just add them up and set them equal to 0. Because we don't want it rotating, right? If that's the center of mass, then this thing isn't rotating around that point. We're getting it. And so that's where that force arrow is going to be. And so let's take a look at this. Well, I'm just going to use the common sense version of this. Instead of adding up and setting them equal to 0, I'm going to take this weight 1 times its distance away. Well, what is that distance right there? How far is that based on these labels that I have down below? And by the way, when I call that x bar, I really mean like that's how far it is to that location. So does it make sense if this distance is x bar right here? If this is this distance, earlier, and x1, does it make sense that this distance right here would be x bar minus x1? Like that's how far it would be. So the moment then on the left side would be weight 1 times x bar minus x1. And then I need the right side to balance, right? And what would its distance be? What's that distance right there? x2 minus x bar. So weight 2 times x2 minus x bar. And so if those were equal, then it'd balance, right? Again, think kids on a teeter-totter. That kid on one side. By the way, based on my drawing, which one does the big kid go on? Is he at weight 2 location or weight 1 location? He's at 2 because he has a small lever arm distance, right? Big kids at weight 2, small kids at weight 1. This could actually work, right? And so if those are equal, then we're balancing and then we can teeter-totter, so to speak. One kid could push with his legs and everything would kind of work. Well, remember what we're actually curious about is what's X bar? In other words, where's that located? What's that distance? Well, can we do the algebra to solve that for X bar? That's not hard, right? So let's see if I multiply weight 1 in there times X bar and weight 1 in there times distance X1 and do the same thing on the other side. Screwed up. Interrupt if there's anything bothering you. That's a good question. Who knows? Who knows? The air is pressurized. So there's a regulator on it and it actually adjusts the pressure of the air you breathe to match the depth you're at.
Does it also help to kind of counteract the pressure down there as well?
Exactly. So you don't even notice it. You could be 100 feet down, and because it's the pressure of the air you're breathing matches the pressure on the outside, then you don't notice it. The downside of that is you don't notice you're breathing pressurized air, but that changes the chemistry of your body. And so if you rip to the surface and suddenly start breathing normal air, then that extra oxygen that's packed in there comes out of the blood in bubble form, and now your joints are all screwed up. So that's what's called the bends. And so when you come back up, you got to come up really slow to kind of get it back to normal air. So you don't even notice it when you're breathing it. It just feels the same to you. So how come fish can breathe? How come fish are fine? They don't have scuba tanks. The water's inside them and outside of them. So it's equal pressure. Yeah.
So if that's true, we're getting theoretical now. Why can't the bluegill survive at the bottom of the ocean?
Why can't they?
Yeah.
Well, there may be other reasons, but it's not because they're getting crushed.
Is that the oxygen in the water where they breathe in? Because they absorb the oxygen off the water.
Right. Like some animals have to come to the surface to breathe, and other ones can just get their oxygen out of the air. Yep. Now you might die because of but if they were able to pressurize the air enough, it'd have to be a huge oxygen tank that wouldn't explode, because if you put too much pressurized air in it, it'll actually blow up at some point because the steel's not strong enough to contain it. But yeah, theoretically, you can dive 1,000 feet down. So the diving bells are actually made out of steel that is thick enough that they don't have to pump pressurized air into it. They just make it strong enough that it won't crush. But can you appreciate if you had an empty pop can, not a can, but the plastic when you put the lid on it and then you put it down underwater, what's going to happen to it? It's going to crush. Interestingly, I took one of those to the top of Mount Shasta because like Pepsi man, you drink Pepsi. Well, I kind of knew that. So I got up to the top and it's like time to celebrate. And so, I cracked the top, but I realized the pressure's changed. So I'm cracking it kind of slow and, finally it's cool and I drink it. And then I put the cap back on, threw it back in my bag, and then I went home. What happened? What did I find when I got home? Smashed, utterly smashed, because there's not as much air weight. You don't think of air as having weight, but I was 28,000 feet and this is 1,000 feet. So, sorry, 14,000 feet. It's 14,000 feet. 28 is like Everest. So it's like 14,000 feet up there. I forgot, is it 12 or 14? Anyway. I dropped top of Mount Shasta. I think it's 14. But you don't think of air as having weight, but it has weight too. Like we swim in the air, fish swim in the water. It actually has a weight. I think isn't it 14.7 pounds per foot is the weight of air?
So the world air is actually triangular loaded.
What's that?
Air is like a triangular loaded.
Yeah. If it's on something that's sideways, yeah. So when I was up in the air, I didn't have near as much both oxygen and air pressure. So it's lighter air pressure. So when I enclosed that air pressure at that level, then I came back down again to a higher pressure, it was like going deeper in the water. And it wasn't just like a little smashed, it was like smashed, there was like nothing inside it. It was like airless. I couldn't believe it. I was like, "Wow, that's really weird." Anyway, what were we doing? Solving for X. Okay, so if I,
Thanks, Tom. Solving for X.
no, I love that. You guys could, we used to have this teacher in high school. We'd get him distracted.
If you were to somehow able to hold your breath from the top of Mount Shasta to the bottom.
Yeah, that would have the same problem.
Like,
You'd be crushing. And now, is your structure of your body, would it be able to withstand that better than a pop bottle? I would think it would, but I think that'd be rough. I think you'd feel that.
Well, Ian's built there, so.
Yeah. You could hold your breath all the way down, couldn't you? All you gotta do is take skis up there and when you get to the top, just tuck it, man. Boom, you could be at the bottom in 30 seconds.
Isn't it when you go up elevations, when you start running around, you get tired faster?
Yeah, because there's less oxygen. You can't get as much oxygen up there.
I hiked this mountain in Wyoming. That was like 12,000. I was not prepared for that.
Yeah, that mountain blew me away because when you get to 10,000 feet, you don't really notice it. But there's a last ridge up there. It's called Misery Ridge. And you can walk like 2 steps and then you have to stop and huff and puff to get your breath back. And once you stop, you're actually perfectly fine. When I was sitting on the top, I was perfectly fine. But if you exert yourself at all, you start just breathing ridiculously hard. I mean, it's like literally walking up 3 steps here, stop and breathe. It was
That's
weird.
kind of funny.
Yeah, I didn't expect that either.
You gotta train that.
Well, are we there algebraically? If I factor X bar out of this and I get W1, that's not right. Are we there? Are you kind of going, okay, I got this now? So final equation, X bar can be found by taking W1 times X1 plus W2 times X2 and dividing by weight 1 plus weight 2. Yeah,
What if you replaced the X bar minus X1 with just one variable, same thing with the other side, and then make it equal that?
yeah, you could totally do that. What I'm trying to do here is do kind of the most general case. Like if you were going to do this, you should make the sum of the moments around one of these 2 points, right? Isn't that what we always did? We chose the end of the beam and that would make the calculation go a little quicker. But the reason I did it this way is because this works every time and it solves a lot of our problems. But what you got to stop and recognize is what did we just write there? What are those right there? If you take a weight times the distance, what are you finding? You're finding torque or moment. So this is actually the sum of the moments. So in our section, well, we just don't have weight 1 and weight 2. We have weight 1, weight 2, weight 3, weight 4, weight 5, weight 6. We got millions of moments and we got to add them all up. How do you add up lots of things? Calc 2, an integral. What is this on the bottom? Yeah, those are just forces. It's the sum of the forces. So basically that's our formula right there. That's our formula for how to figure this out. Go ahead.
This is similar to one of the equations in physics with the gravitational forces.
Yes, that's exactly right. This particular formula shows up quite a bit. You're 100% right. So I could actually say then that X bar is equal to X times the weight as a function of X. In other words, where, I'll show you what I mean by that in a second, but X is like, where are you? In other words, look at your forces right here in our problem. You have 18 feet to work with. Well, where are you right now? Like X is, well, right there, but then I'm going to move it to somewhere else and somewhere else and somewhere else. But so that X will be my distance. But then the second thing I'm going to have to figure out is like, what's the force right there? So it's, and that force will be, well, you know, we don't know because it's in some random location. As we said, we know what it is in the middle. It'll be 120, but we don't know what it is at some random location. So I'm literally going to have to add up every one of those forces times every one of those lengths. Thank God for integrals, or I would actually have to do that. So all we do with calculus is say we use the integral sign for adding them all up, which basically means I have infinitely many of them and I won't have to add them, which is really cool. So there's the sum of the moments And then down here is just the sum of the, well, the weights themselves. I have to add up every single one of those weights. So in a sense, this is kind of our cool formula for doing this. Now, the neat thing is, as I said, a triangular load is going to have a nice fractional location, and we can just memorize that and then never do this again. You understand that? We're going to discover in a minute that it's 2/3 of the way over. And so when we know that, then we just say, oh, the load's 2/3 of the way over, and we're done. Like, we don't have to do integration every time. And so as a mathematician, and also to kind of justify all the calculus you've studied, I want to show you where 2/3 comes from, because it's kind of cool. And also to help you understand, if you ever had some really crazy load, you could actually do calculus and locate it. Maybe it's a weird load that no one's ever seen before. You're like the first one that's ever done it. And so this is the theoretical background behind how that works. Okay, so unpause. Let's go back to our problem then. That's why I can't do this without an iPad anymore. I know, waste your precious life, man. We can't have that. Now, here's what's cool though. What we got to come up with is an equation that tells us, based on where our X happens to be, what the load is right there. In other words, I'm at X right now at some random location, and I need to know what is this weight right here, right? I need to know what that is. And so we know it's between 0 and 240, and we can kind of estimate it, but we got to get it exactly right. Well, the cool thing is it's just an equation of a line. So if I think of this right here as the XY axis, and so I put this line right there at 0, then this is an equation, y equals mx plus b. And the b is actually 0 because there's no y-intercept, since I put it in a location to make my life easy, right? M is the slope. Well, what's the slope of that line? Isn't it a run of 18? Oops, that was the wrong thing. Isn't it a run of 18 and a rise of 240? Now, those are weird units, aren't they? So in our problem, it's 240 over 18 x. So there's the equation of our, that's how you figure it out. Now, maybe we're lucky and 240 divided by 18 is a nice number. Is it? No, 13 1/3. So I'll just leave it alone. So now let's just check and see if that works. Does this formula work? Well, if I put in 0 for x distance, then I get 0 for a force. Yeah, that makes sense, because that's what was happening over here. What if you put 18 in for your length? In other words, you're right here. 18's cancel. Yeah, I get 240. Does the middle work? We know the middle is supposed to be 120. The middle would be x is 9, right? So my x distance is 9. 9 and 18 is 2, and then 240 divided by 2, it's working. Do you see that? I get 120. So this is working. This tells me the weight anytime I want. And so I have this formula for the weight. Okay, cool. So can't I find x bar then? X bar, we said, is the sum of x times the weight as a function of x. And this is just the sum of weight times x. So let's work that out. So for us, that means integral of x times 240 over 18x. You cool with that? Those don't cancel. What do?
I'm saying move them out outside of the integral.
No, the 240 over 18 can go outside of the integral. So let's do the bottom one first. So yeah, because 240 over 18 is a constant, we're just taking the integral of x. Who remembers their rules for integrals? How do I take the integral of x to the first? Yeah, you raise the power of the exponent 1, and then you divide by that exponent. So it's x squared over 2 or 1/2 x squared. And now, what am I evaluating this between? Where does x live? Because I should have written this in earlier. X's go from everywhere from 18 to 0, don't they? So I want that x to move its way everywhere from 18 to 0. So now I can, and since 0 just means nothing, I basically stick 18 in there. So do this in your calculator. 240 over 18 times 18 squared divided by 2. What do you get? This is too cool to blaze by. We got to slow down and understand this. Blurt it out.
You say 240 over 18 times 18.
18 squared over 2. Like that's the formula that we have left here,
I
right?
got 56.57.
I don't think that's right. I'm not sure, but. $21.60. Is that a coincidence that earlier we figured out all the forces were 2160 using the area of a triangle? It's not. Now remember, what does integral do? It tells you the area under something. Well, that was a triangle. Do we need calculus to find the area of a triangle? No, we got a formula, 1/2 length times height squared. So the fact that we got 2160 earlier, we actually did not have to use calculus to get 2160 there. But that's because this is just a line. You have an assignment question, if I remember right, that looks something like this. Like you have a beam, except for the load on it is like a parabola. Because I don't have any real engineering experience, I don't even know where you would find such a load. Is it possible to have a load that's parabolic? Is that even possible? If I had more experience, I have a feeling there'd be an answer to that. But ours is just a triangle, so we could have just found, we didn't have to do calculus on the bottom of that. So we already had that number, right? We didn't need that number. Actually, what we need is the top. And so let's go calculate the top. We do need the top. And so what I want you to pay attention to is actually where does that actually land? So the top is from 18 to 0. And we end up with 240 over 18, but it's now x times x or x squared. And just like last time, I could make my life a little easier by recognizing that constant can sit out front. And so I just have the integral of x squared. Well, the power rule says you add 1 to that power, so it becomes x cubed, and then you divide by 3. So same thing, stick 18 in there. What do you get? You should have that whole thing typed in. All you should need to do is go back and change the squared to a cubed and divide by 3. I got 25,920 for that. Did I get it right?
Mine equals 2/3. That's what I thought I got. Oh, wait, isn't that the top one?
Yeah, that's the top. That's the top one. So basically this is the sum of the moments. And this is the sum of the forces, or the sum of the weights. So what is x bar? 25,920 divided by 2160. What do you get? Yep, you get 12. That's exactly right. Now let's go back and put the units in here. Since these are moments, isn't this unit foot-pounds? And since this is weights, isn't this pounds? And so if I took foot-pounds divided by pounds, wouldn't that be feet? So we now know where to locate it. You see what I'm saying? So we come over 12 feet, my friends. And that's where we put our 2160. We have one force and now we know where it goes. Now, what do you notice about 12 and 18? That's 2/3 of the way over. So what I'm not going to do, if I went back and redid this, except for I called 240 like W, like a variable, and then this 18, I called it L, and I redid the problem, but I treated W and L like constants because they're going to be constants, then you would actually get 2/3 L. You wouldn't get 12, you'd get 2/3 of, well, 18, 2/3 of L. And so that's where the 2/3 comes from. So I'll leave it at that. I'm sort of, as a mathematician, I'm tempted to go back and do this again, but this isn't a math class. So what's the key conclusion? Two-thirds of the way over for a triangular load. And of course, triangular, of course, that's 2/3 from the short side, right? That'd be 1/3 from the long side. So you got to think about that a little bit, right? So that means we don't have to do this again. If we have a triangular load, you know how to use area calculations to figure out the total force. And then you just put it 2/3 of the way over.
So 2/3 from the long side.
So it's really 2/3 over from the short side, right?
Well,
From the left to the right.
are we going from left to right?
Well, you can't say left to right because
Well, we started
it's
with
left
that.
to right in this picture, but what if the triangular load had the tall side on the other side? You see what I mean? So I can't say left and right. I got to say from the short side. Go ahead, Ian.
In real life, would a triangular load really be a perfect triangle, or would it actually kind of?
Well, it is in the case of water backed up against a dam. It's perfectly triangular because every foot you go down, it gets 8 pounds heavier. So it's really linear. And the same is true for dirt. You go every foot, it's actually perfectly triangular. Yeah. So that's interesting. Okay. Thou hast been introduced. What time is it? Yeah, we're okay.
There was another thing on that equation. Basically, you can take out the slope out to the side and then cancel it out before you do the integral.
Say that one more time.
When you do up the equations with the integral, you know how you can take out the constant out or the
Yeah.
2040?
Yeah.
And you did that to the bottom as well. It would cancel out.
Yeah,
So that would make the slope irrelevant.
that's interesting. Let me think about that.
And then the both the integrals can take out the 240 divided by 18 onto the front. And then since one's on top of the other, they cancel out. Obviously, fractions, you infer them and they cancel each other out. So then you're left with on the top integral of x squared dx, and on the bottom integral of x dx.
Actually, let's play with that for just a second. Everybody agree with what he said? He's exactly right. This never occurred to me before, but let's just play with that and see if that goes anywhere. So I ended up then effectively dividing. If I think of the 18 as L instead of 18, like it doesn't have to be 18, right? It could be anything. And then you just observe the slope cancels out, then don't I have x cubed over 3 divided by x squared over 2? Except for when I plug 18 in. So those are actually numbers, but I'm going to stick L in there. What does that reduce to?
Two-thirds out.
2/3 L. So I was thinking I'd have to start over and like waste 20 minutes, but because of Caesar's brilliant observation about those slopes actually canceling out, you can actually see 2/3 L right here sort of show up. But again, notice 2/3 L, how is that measured? Well, from the XY axis that I drew, it's like measured from the left in this drawing. But remember, couldn't you have a beam where the triangular load was this way? Like you can't always, You can't always say it's from the left. Does that make sense? Because you can switch it around. So it's really 2/3 from the short side or 1/3 from the long side is really the takeaway. Okay, so let's apply that to this question. Notice what kind of load is that though? That's kind of triangular, but it doesn't go to 0. So it's not 2/3 of the way over. The problem is that's a rectangular load and a triangular load. It's actually, what is that, a trapezoid? Yeah, it's like a trapezoidal load. That's actually also really common.
Rectangle and triangle.
Exactly. So this actually isn't terrible. There's not just and we probably could make a formula for this, but if we just treat it as a rectangle and a triangle, it's going to be easy. But we're going to get 2 forces. So anyway, I don't even know what it's asking. Replace the loading by an equivalent resultant force and locate it. So again, when you see those arrows, you have to represent, they can't really draw infinitely many arrows or it'd be solid black and you wouldn't even know what was going on. But maybe you saw that in the BC Calc. I think I mentioned it at the time, but when I designed beams, those arrows are actually on top of the beam, telling whoever's looking at it, this is a uniform distributed load. Okay, so yeah, that's all we have to do is just think of this as a rectangle plus a triangle. So notice this is in metric, and notice it's not pounds per foot, it's kilonewtons per meter, or it could be newtons per meter, but it's kilonewtons per meter. So there's my rectangle. Would you agree for the rectangle? I have 2 kilonewtons per meter times all the way across. Isn't that 6 meters? Notice in this particular case, I don't even have to care about the supports underneath it. But remember, the long-term goal here would be to figure out how much A and B are going to have to support. Do you understand that? I need to know how much force is on A and how much force is on B because I got to bolt those to something and make sure it doesn't fall off. So number one, I don't even know how much force that is because there's infinitely many forces up there. But I also don't know, how much is going to go to each one. And so by me being able to reduce this to just a couple of forces, then I will be able to make that calculation. So if I take 2 kilonewtons per meter times 6 meters, then that's just 12 kilonewtons. And of course, its location would be right in the center because that's a triangular load. I don't have to do any calculations for that. You cool with that? What about the triangular load? Well, because this triangular load is 2 and this side is 5, then really that means that top portion of it is 3. You with me there? So just like I found the area of the rectangle a second ago by going 2 kilonewtons per meter times 6, I'm going to do the same thing. I have 3 kilonewtons per meter times a distance of 6 meters, but then times a half because it's a triangle. So that's half of 18, which is 9. So I have 9 kilonewtons. Notice I did not need to do calculus to come up with that. Even though there was infinitely many forces, I could do calculus to find the area under that curve, but I didn't have to. So do you agree then that my 9 kilonewton force would be right there in the center? Since that's 6 meters, that'd be 3 meters from both sides. That's where my 9, I'm sorry, I screwed that up, 12. It's not meters, it's kilonewtons. This is where my 12 kilonewton force would be, right in the center. You agree with that? My 9 kilonewton force would be where? It's from the short side, 2/3 of 6, which is 4. So it's actually right over the top of this support. Tracking with that? So there, cool. I used to have infinitely many forces. Now I just have 2. And so would you agree now that if you did the sum of the moments around A, you could actually figure out how much of that, well, notice we now know there's 21 kilonewtons there. We never knew there was how much force that was because there's infinitely many forces there. But now we know it's 21 kilonewtons. And we weren't able to break it into just one. However, could we keep going based on the sum of the moments and actually turn that into 21 kilonewtons and put it in a certain location? We could, but I think that's a waste of time because we got it down to 2. So couldn't we just do some of the moments around A right now and figure out how much of that 21 is at B, and then we would know how much is at A, and then we could continue our design. Now in this case, they just said, you're done, you don't have to do that. So a better problem would have been determine the reactions at A and B, which is the same thing we just did, we're just not done. So thanks to the fact that we knew that 9 was 2/3 of the way over, notice we never had to come up with an equation for that line. We didn't have to say, you know, W equals, what is that, 3/6x or something. We didn't have to come up with that because we didn't need calculus, because calculus told us it was 2/3 of the way over, so we didn't need to do calculus. That's kind of cool. So again, I find this interesting as a teacher because it's like, do you need calculus? Yes, but usually it produces a formula that's an algebra formula, and then you don't need calculus after that. But it's saving you a crap load of time. So you sort of do need calculus, but sometimes it's some nerd, you know, that lived 100 years ago that already figured it out, and then we just live on their knowledge, their wisdom. So just to have this in the notes, this would be 3 meters over to there. And since the other one's right on the top of it, I'll just leave that one off. Oh, notice we aren't off the hook yet. So as I said, if I was finding the reactions, I'd be done, but they didn't say, they said replace this loading by an equivalent resultant force, like singular. So if I looked in the back of the book, that wouldn't be it. They actually want us to make it one force. And so I guess I do have to keep going. So the force then would actually be equal to 9 plus 12, which is 21, as I said. But notice they said, you're not done. You got to tell me where to put that.
Put in the distance, leave the difference between both of the forces being applied. The one's at 3, the other one's at 4. So the 3.5.
Well, one way to do it would be this. So you're sort of reasoning out what you think it would be, but and you might be right. But here's what I'm thinking. Is this the easiest way? If this is A over here and I've got 12 there and 9 here, and I'm ultimately trying to figure out, and it sort of feels like it would be in the middle of these two, doesn't it? I mean, it kind of feels like it'd be, but it won't be perfectly in the middle because 12 and 9 aren't the same size. It'd actually be a little closer to 9, wouldn't it? But I'm thinking that resultant force of 21 would be maybe right there. But of course, the question is, where is there, right? Well, I'm thinking if I did the sum of the moments around A, well, maybe I don't even do the sum of the moments. I'm just going to do this kind of based on logic. So those two moments would have to be equal. Do you agree with that? Now, I don't know if you know what I mean when I say moments, but if I take 12 times its distance of 3 plus 9 times its distance of 4, wouldn't that have to equal 21 times its distance of D? They're equal, in other words. Now, I could have added them and set them equal to 0. I could have taken that approach, but I'm just thinking of this as teeter-totter-ish. So that's 36 and 36, which is 72. 72 divided by 21. I got D is, well, in a weird location. It's 3.4243 meters. So it is between the two. And it is a hair closer to 12. Do you see that? 3.5 would have put it right in the center. But 3.43 is a hair to the left, but it's in a location I never would have guessed. So now I think I'm actually done given what they asked. How you doing? Are you okay? Okay. I'll come answer it right now. So I want you to stare now this beauty. Actually, you can stare at it. It's right in front of you, but I want to know what you would do with this one. Yeah, it's just two triangles. So think about that for a second. Actually, try to make a little progress with it. It's okay to write on your paper and be wrong. So I'm going to post what I do anyway. So yours is wrong. All right. Well, they have a minimum loss rate.
You end up getting 567. You end up getting 567. Okay, because all my kids, you got.
So if I ask you to do a little explanation,
You could. Wherever the light comes up with the wrong one, or putting down the registration stuff.
yeah, they're about to.
Water dish with a cat outside. Been frozen the last couple of days. In the ice. It's a 500 kilonewtons with rotation. Wanting to rotate.
Yeah, notice they threw in like a moment. They threw in a 500 kilonewton moment. So not only is there this infinitely many triangular forces, but they said there's also a moment thrown into this from who the heck knows where.
So it's only a point on the center of mass of the force, or is it?
So it's only around O.
We still need to find the center of mass, and then when we do the moment of low.
Yeah.
We can use we basically have to do what we did on the previous one, find our resulting force. And then add it with pressure factor with some 500. No, add it with 500 and the
That's right. And there's also a 15 kilonewton load. There's also a 15 kilonewton load over on the right that also is just coming from nowhere.
Oh, yeah, no, we also. But then on that, that's a pin. So we didn't have a force going up as well.
Well, that's the reactions. In other words, right now, all we have is all the forces that are on it. And what engineers call reactions is what's happening at O and over at the other side in response. So if we knew that was a total of, 50 kilonewtons up there or something, then we would say, oh, what's happening at O and the other side to counteract that 50? So-
Force will have the size right there on that. I mean, on the pin connection.
So the result of this is there's going to have to be some force over here
Or to balance it.
and some force over there. That would be the reactions. And so that's why they're showing pins there, because that if all the forces are down, then that beam is flying through the air.
Hey, Doug,
Yes.
so for our location, like for the left triangle, these are two triangles, right?
Yeah.
Location for the left triangle is D, and then for our second triangle on the right, we put our location as 7.5 plus D, like where we get.
Well, you should think of it as two triangles and if you look just at this one, you're thinking of it as 2/3 of the way over this way. That's where it's located. And then the same over here, except it's going the other direction because,
But let's say you get 2, right? So it's 2 going inward from that. You add, I guess it's not 2, right? It's like 10, because it's 7.5 plus 2. Is that how you?
Well, once you find the center of mass on each one, then you can
Because
pick
we're-
one side to be your origin.
yeah, you're making it too complicated. Just take 2/3 of 4.5 and figure out what that measurement is. Doesn't matter if it's measured from the left or the right, as long as you have it written in there.
We're saying adding the left side to this is-
Mhm.
Yeah, I think.
Now, you're right, you are gonna need to know the distance from the left ultimately, because
Right.
maybe you're gonna do a moment calculation, but as long as you have the dimension of it on there somewhere, then.
Okay.
So no rectangular forces, that's cool.
So what's this question asking for?
Same as last time. It wants, like, right now we have a 15 kilonewton force. And then we're about to have two more, one for each triangle. And in one sense, we could say, okay, we're done. We used to have millions of forces. Now we just have three. I'm done. But they're saying, no, even go further, like get it down to one. I think in the real world, that'd be a waste of time because I can do moment calculations with three forces. Like, that's fine. Seems like a lot of work to go from 3 to 1. It's like I can handle 3. I just can't handle 50.
So
All right.
this kind of moment, like 500 kilonewton per meter is almost just like, how do we?
So that's nowhere as far as force.
Right.
That's only in the moment calculation, which I wouldn't care about based on what I just said, except for they're saying, sorry, you can't even have 3 forces. You got to have 1. And so I'm gonna have to do a moment calculation like we did a minute ago in order to reduce 3 forces to 1. And then when I do the moment calculation, then 500 is going to be in there.
Couldn't we just do what you did though and say 22.5 times this distance plus 13.5 times this distance plus 15 times this distance
Yes.
equals whatever d.
Yeah, that's
So then
right.
that 500 becomes irrelevant.
Well, it's going to be a part of the rotation though. It's in there.
Yeah.
It's adding to that. So I'm going to need to add 500 to what you just said, and then I can solve for D.
But if it's the moment around O,
Yeah.
Yeah, and that's because we're doing the moment around O. Okay, so let's scope this out. Let's do this together. So would you agree the force on the left side? I'm going to title this left. The force on that side, or the weight, would be, well, its height is 6 and its distance is 7.5 and times a half. Notice it's kilonewton meters times meters, so this is going to end up kilonewtons. So I get 22.5 kilonewtons. Do you understand where that's located? Eyeballing it, that'd be about here, 2/3 of the way over. Well, 2/3 of 7.5 is 5. So I might as well add that in here. You agree with that? So I have the weight. I used to have a billion forces. Now I just have one, 22.5, and I know where it is. 2/3 of the way over from the short side. Same thing on the other side. What about the right side? The peak is still 6. So the force over there, I'll call it force 1 and force 2, weight 1 and weight 2, if I have some reason to do that later on. 6 times, oh, a much smaller distance, 4.5, but it's a triangle, so I'm finding area. That's 13.5 kilonewtons. Much smaller. Why is it smaller? Because it's shorter. There's not as many forces, if you will. It still starts at 6, but it's just not as long. Again, that would be 2/3 of the way in from the short side. So I'm thinking that looks to be about here, maybe somewhere in there. So do you agree that I now have it down to 3 forces? And as I said, the real world, you should just quit right there. Like you could do the sum of the moments around O and actually put this reaction force in here. I'll call that reaction 2. If you did the sum of the moments around O and set it equal to 0, you'd be able to solve for that reaction, which is the only reason you're doing this anyway. There's no real reason to reduce it to 1 force. 3 is plenty enough. So in the real world, my next calculation would be the sum of the moments around O. I've now got my free body diagram in a sense because I added that R2 over there, and I'd actually be able to figure out. Notice I know I have 15 plus 22.5 plus 13.5. I now know how much total load is up there, which I again didn't know before. And it's just a question of how much is it at O and how much is it over there at R2. But they're saying, could you reduce it to 1? Fine, I can do that if you want me to, but it's dumb. But I'm going to use the same technique. So, and because this feels a little more confusing than the last problem, I find myself wanting to like find the sum of the moments around O and set it equal to 0 and think of some as positive and some as negative and so forth. But again, the thing that troubles me about that is, don't I need my free, I mean, this is what's bothering me. Don't I need that don't I need that in there to do this? Because I'm not gonna get 0, because aren't they all trying to get it to rotate? So that's actually kind of bothering me right now. I actually don't know what the answer to that is. So maybe I can't do that. Let's do what we did last time. So notice I have sort of those 3 forces all pushing down. But what I'm trying to do is replace it with one huge one. And remember, as I said, you can have this all together, 22.5 plus 13.5 plus 15. That's 51. So I'm changing colors here. I'm just guessing. I actually really don't have much of a feel. 22.5 is the biggest one. So I'm feeling like that one's got a lot of weight. 13 is like half that, but then there's 15. And so I'm kind of thinking, oh, maybe it's about right there. So I'm basically saying all the blue forces, if I go back and change this one to blue, I'm sort of trying to get the blues to equal the red now. So instead of setting them equal to 0, because again, that's bothering me because they're all pushing down. They're all trying to get it to rotate negatively. So I'm not going to be able to set it equal to 0. So let's see what we get for that. So the moments, I need equal moments, I guess, is the way I'll word this, equal moments. So what do I have? I have 22.5 times its distance from O, which is 5. Notice I'm leaving the units off because I'm noticing every one of them is kilonewtons times meters. So that's okay. And then I've got added to that 13.5 times its distance. I never wrote that distance in earlier, but 2/3 of 4.5 is 3, isn't it? So since the overall distance here is 12, if I'm 3 from the right of 12, then I'd be at 9, wouldn't I? And then I've also got that 15, and it's a distance of, well, all the way across, it's 12. And then that would have to be equal to the red one, right? The red one is 51 kilonewtons, and it's times some distance d that I don't know. Yeah, 22.5. We got it down to 3 forces, 22.5, 13.5, and 15. I just added all those up. Thanks for speaking up. I love it. So does it make sense that if those two are supposed to be equal to, if those have to be equal, and I'm trying to get it down to 1 force, that 1 force would be 51, but I just don't know where it is. So in the end, let's see what I get for that. 22.5 times 5 plus 13.5. What am I missing, by the way? I'm missing something I just remembered. They threw another rotation in there, right? That just kind of came from nowhere. So basically that means it's rotating even harder. That's going to make my distance a little bigger. Does that make sense? Because it's going to have to get, my 51 is going to have to be further away to give me enough moment to counteract that. So I got to go back and add that in. I forgot that. Notice its unit is also kilonewton meters, just like the rest of ours would be. Is 500 a really big contribution to this discussion, or is it like, that's not that much? It's massive, because 15 times 12 is like, what is that, 150? That's like 3 times as much as that one. So that was a pretty big contribution to this. So it looks like I typed everything in right. I got something that makes no sense. I got 440.
So this is the, I got 16.
I'm sure I just did something stupid.
This 500 is nothing.
Yeah.
You need to subtract the 15, well, I mean, you need to take it out of the equation because you already have it added on 51. No, because I did it different and I got a 8.117, but that's
Yeah.
because I didn't add the 15 with my resultant force. I only did the 22.5 and the 13.5 on the distance of that. Then I did the moment, or not the moment, and then I did 36 my resultant force was 36 and the distance was 6.5. And then added the 15 times 12 distance, equal to 51 D. And D was 8.11764, and it kept going.
I'm trying to figure out where you and I got something different. I think I'm correct.
I didn't necessarily go through those steps.
Actually, I'm not correct.
8.11 is if you don't have the 500.
Yeah. Yeah, that's exactly right. I didn't do moment of zero. I just, yeah, that's what he said.
Distance from 13.5 to 9.
No, it's for mine is, oh yeah, it is.
No, it's supposed to be, because it's your.
Oh, yeah. Oh, so
Yeah. Taking out the 500, and that's what I got.
It's 3 short.
I typed stuff in wrong like 3 times here, but I think I actually have this right now.
So that's what I was wondering, 17, so this is like off the page.
That's exactly right. That force would actually have to be off the page. Is that okay? Yeah, it is. Why is it off the page? The dumb 500 that got thrown in there. So the 500 was significant. You agree with that? And that made the distance have to get longer because 51 is 51. But if you want to make more moment, you got to make a bigger distance. And so that pushed it clear off the page.
So does that mean this thing's like, or is it? It's not even on?
No, it just means if we proceeded to the reactions, it means if I called this point A over here, it just means the force at A is going to be massive. Like it'll be 50 of the 51 newtons. As a matter of fact,
12 times force is equal to.
actually, I think we need to calculate that because it's cool. I think this is actually worth doing. So I think we need to do this. So let's now do the sum of the moments just for the fun of it around O. Would you agree that we start out with a negative 500 because that 500 is trying to rotate it clockwise? And we now just discovered we have 51 times 17.92, right? Because we only have one force. And you see why I'm saying it's a waste of time? Because I could have saved all this trouble and just done it with the other 3 forces. And then finally, if I call this force at A, then we have the force of A stopping that, right? That's the only, so our free body diagram would be incomplete without that. And so then I can say, oh, well, there's my plus, it's force of A, and it's located a distance of 12 away, right? And this would need to be 0. Now remember, the total force coming down on this thing is 51, right? What do you get for the force of A?
117.
Yep, that's what I got. This is really interesting. That should bother you immensely. Why should it bother you? How much force did we have total coming down?
51 total, so it's over double that.
What? How could it be more than 51?
Because of
The
that,
turning moment of the 500 and right on the side of it.
Wait, I'm sorry.
Because isn't that 500 rotation added every single way as it goes across?
yeah, so
So that just means that you have to have a really, really strong.
Now think about this. If your force is actually out here at 51 newtons, and let's kind of pretend this was attached in such a way that it could actually affect the beam. Because remember, in a sense, you look out there and goes, well, it's not touching anything.
So can you shorten that basically by having a strong enough point that the 15 is?
That's where we're doing.
So think about this. If you push down here on a beam that was connected like this, what's going to happen to that side? It's going to go up. So this force over here is actually going the wrong direction. It's actually down. So it's going to have to hold down on something, which is very interesting if you look at the drawing, because how is that attached over there? That's just sitting on something. It's not actually attached, which means this isn't going to work. Like that'll break. Isn't that interesting? Like that needed to be pin connected over there.
That's the hardest ones.
It's your job to know
understand,
this
so the ones
stuff.
that just don't work.
Yeah, this is
Like-
fascinating.
Like once something stops working, you're just like, wait, what's going on?
So just to stick this in the notes.
Because the structure was very long.
Yeah, but
It's a hypothetical kind of thing.
so what would work?
51 down,
This wouldn't have-
117.8 up.
Even if this point is extremely strong.
Oh, no, because O would have flipped.
So what we just realized, if we drew in what we would normally draw, then we would say, oh, force O is actually going up, because we think of those as always needing to support the 51. We're used to two numbers that add to 51, maybe one's bigger than the other. But when you try to solve this, you actually get force of 0 is negative something, right? You actually get negative 66.8
So then the force would be down.
kilonewtons, which actually means you got the arrow going the wrong direction. And that makes sense when you draw this picture over here.
But it's not even, yeah, or the, it has to be attached.
Oh, you're saying this is.
Because it's on.
Or something other weight on top of it pushing down. Like both things.
Yeah, something pushing down, or more likely an attachment that's, you know, a pin attachment that's,
The force is wanting it to flip.
Yeah, that doesn't make sense because there's no way that it's just gonna go magically stand up.
The only reason
Oh,
you're having.
imagine someone's pushing 500 force to make it.
Yeah. But I'm just like what's pushing?
The 500.
The
But where's the 500?
imagination.
That's why you're having trouble with this.
It's the 500, yeah.
The 500.
imagination.
the 500 was a significant magical introduction. It's like some, you know, God is up there going, I'm gonna twist this, you know, and screw it all up. So yeah, in a sense, I kind of wish the 500 wasn't there, but it's kind of cool to see it just because it's weird that it actually put that force off the picture, and that's legit. That doesn't mean you made a mistake. My first thought was I made a mistake, but it actually doesn't mean you do, and it's the 500 that caused that. If the 500 wasn't there, it would have been in the middle someplace right where I drew it. But at the time, and notice I drew it in the wrong spot because I was really not thinking about the 500. I wasn't thinking, is that a big contribution or a small contribution? So, you know, in the end, I missed its location by a mile.
So how would this be shown, I guess, in the real world? So we now know that this moment is like wanting, we now know that we need to pin or like bolt O down, moment O.
Yeah,
How would that show in like your software, I guess? Because like, obviously we found it with all this math, and I guess logically we can
Yeah.
kind of think about it, but like,
the only reason you even look at this problem is to figure out the reactions at A and O, because you're the one that's going to have to decide how those are connected. Am I going to pin connect them? Am I going to weld them? Am I going to bolt them? And then it's sort of a surprise, like, oh, well, that left side is actually not being supported this way. It's actually the other way. And so it's like, oh, that rules out just being simply supported like it is, like sitting on something. Oh, I didn't realize that. So can't put a roller on it like they drew there. So it's really just about you doing the math to make it happen. Nobody cares about all these calculations. They just want to know what those two supports are. What are they? How many bolts? You know, you got to design that. So given that that left side actually wants to lift up with 66 kilonewtons, how many bolts do you, I mean, if I'm screwing it into wood, how many screws do I need to put into the wood before screws don't rip through the wood? 10, 6? Do I use lag bolts? They're 7 inches long. Do I use lag bolts that are 3 inches long? Like how much grab? How do I do that? And then also, do you realize there's a workmanship component to that? If it was wood and they drilled too big of a hole so that the threads didn't grab as much wood as they should, like it could fail because of that. Woo.
This is
There's a lot to think about,
thing
right?
about a coarse thread and fine thread. Which one goes more strength?
Right, fine threads, coarse threads.
What is that issue? Or,
And then even then, all wood's different. Like there's strong wood and weak wood. And so if you sort of you'd have to have a big factor of safety. If you decided you needed 4 lag bolts, you should put 8, right? Like after all these calculations, we need 4, now double it. That's kind of what would actually happen. Woo! Steam and brain. All right, fortunately, this last one's easy, although it looks hard. Uh-oh. Uh-oh, the loading is curved.
that means I have a radius.
Well, because it says the equation is x squared, it means that's a parabola. So that's not a circular load. It's a parabolic load, if you will. If that load is weird like this one is, you really don't care as long as you have an equation that defines what the weight is at any given point. Now, there is something you need to look at very carefully here, which is easy to miss, but notice this is the axis right here. Like that's where 0, 0 is. It's not over on the left. They put it 1 foot in for some reason. Like that feels really weird. But one thing you might do really quick is, given that this location right here is at x is -1, then W of -1. W of -1 would be 2 times -1 squared minus 8 times -1 plus 18. What does that give you if you plug that in? Not -2, +2. 2 plus 8 plus 18, 28. That's what it's supposed to be. It said 28 over there, right? So it's like, hey, this seems to be working. If I put in x is 2 at x equals 2, notice they're saying it's 10 pounds right there. That'd be 2 times 2 squared plus, I'm sorry, minus 8 times 2 plus 18. What is that? 8 minus 16, that'd be -8 plus 18, 10. It's working. Like this crazy formula is working. And then of course, if I put 4 in, I'd get 18 on the other side. It seems to be working, right? So that's kind of cool. Do you understand what that formula is telling you? It's telling you how to find the weight no matter where you're located. That's kind of cool. Ian, go ahead. Yeah, so because of this W that they drew up here, this is the origin right there.
It's just like complicate things, but because I always like to have left and right and stuff, everything. But if I move my original to the left and the plus 18 make it plus 28, would that work?
You'd have to, if you move an equation 1, that means you have to replace all the x's with x plus 1. If you moved it left 1, you'd have to replace all the x's with x plus 1, and then it would work.
No, I mean,
As a side note, I'm going to erase this, but would you agree then that this point over here on the left is actually -128? And this point here in the middle is actually 210. And this point over here on the right is actually 418. Do you agree with that? Extra credit, could you come up with that equation yourself? Like if that equation wasn't there, could you come up with it? That's a system of equations. Can you find the equation of a parabola that goes through those 3 points? There's the answer, 2x squared minus 8x plus 18. Could you use a matrix? Could you write 3 equations, 3 unknowns from your math skills and actually have produced that? Did you have to be given that? No, you did not. No, yeah, that's not obvious. Like you could have at one time. I mean, you would have been sort of taught that at one time, but again, that's one of the neat things about taking a class like this, because it is not discriminant about all the math that you've ever learned. It's just kind of assumes it's on board, right? But of course, that would have been mean not to do that. But in the real world, is someone to hand you an equation like that? Like, hey, here's the equation of your loading. No. I don't know where a parabolic load would come from. I am wondering a little bit about like Golden Gate Bridge, because you have cables that hang in a parabola. Would that somehow produce? My gut reaction is no, because the cable just weighs, 10 pounds a foot. So it's just 10 pounds a foot. Even though it's hanging in a parabola, doesn't mean the load is bigger on one side than the other. But I'm just pondering that and wondering. What's that? It is if the road's hanging from it, but if it's just hanging on its own, if it's hanging on its own, then no. Like those power lines out there, that's actually a parabolic load. If you hang a road from it or something, then it turns into a catenary. Or do I have that backwards? I have that backwards. If it's hanging from a road, it's a parabola.
I'm trying to
If
think.
it's hanging by itself, it's catenary.
I was talking to them about your hardest projects. I think it was either maybe the catenary, because I have a really bad taste about that word, or maybe the.
Do you have like a
basketball.
nervospatial tick when that word comes up? Like start
Catenary.
salivating?
The basketball.
Yeah. Life is pain, brother. Gotta get used to it. Okay, so in this case, because we don't have triangles, like we can't cheat to get the area, does that make sense? We've been cheating to get the area because we knew the area of a rectangle and we knew the area of a triangle. We can't cheat here. We actually have to go back to that formula we looked at earlier that told us that the center of mass was ultimately found by integrating x times the weight as a function of x and dividing that by the integral of just all the weights added together. Because in this case, we're not going to be able to cheat to get the sum of the weights. We since cheated a while ago to get 51 for all those weights because we knew the areas of triangles. And we were able to calculate the moments ourselves because we knew where they were located. We said, oh yeah, they're 2/3 of the way over. We do not know where this is located, so we have no choice but to do this using integration because it's a weird shape.
So for X, do we use the quadratic formula on W? Find it?
So we are just thinking of this then as, let's just find, one particular force right here. Well, we'll say that's X over there. And we're going to let X not just be 1 and 2 and 3 and 4, but all the decimals between. So where does X have to go to get to the whole bridge? Right 4 and left 1. So it's got to go from -1 to +4 since they put the axis in such a weird location. So the equation is based on having the origin where this shows. Like if you don't notice that, which would be easy not to notice. So we're not going from 0 to 5 because the axis doesn't start over there at A. So this is all going down, my friends, from -1 to 4. So then I say, okay, cool, I can do that. So that'd be the integral of x times, well, we have an equation for weight as a function of x. It's 2x squared minus 8x plus 18. And we're evaluating that from 4 to -1. And also from 4 to -1, we have just the weight itself. No x, it's not a moment. So we just the x squared minus 8x plus 18. Fortunately, we just reviewed a minute ago, this isn't a hard integral to take because this is just the power rule, the reverse. And so this isn't like, oh no, trig substitution. Like I don't remember, it's like natural log, crap, what was the integral of natural log? That kind of stuff that you wouldn't necessarily remember right off the top of your head. But as an engineer, if you did need that, what would you do? Hey Siri, what's the integral of natural log? That's what you would do, right? Get online, just search it up. Like you don't really need the painful calculus to produce these things. You might even be able to go one step further and kind of just type that integral into CY math or Wolfram alpha. Those are sheets I showed you, and it just produces the answer to this, and you never even have to know what the integral is. Like, just tell me the area, man. Let's get on with it. Do you agree the top one, if I distributed the x in there, they'd all just go up a power? So it wouldn't be 2x squared, it'd be 2x cubed. So on the bottom then, if I raise the x squared to x cubed and then divide by 3, if I raise the 8x to the first to 8x to the second and then divide by 2, that'd really be 4x squared. And then the last 18 is notice 18x to the 0 right now. So if you add 1 to that, it'd be 18x to the 1 divided by 1. So I got to evaluate that at 4 and -1. And when I get that, remember, I'm going to know what the total force is up there. Isn't that really cool to think this is a crazy loading that goes from 28 to 10 to 18? Every one of them is different by some crazy parabola. And I'm about to know the sum of all those forces just from that alone. I mean, that feels cool to me. So I'm going to do that right now just because I want to know. 2 times 4 raised to the 3rd divided by 3 minus 4 times 4 squared minus 18 times 4. I got negative 93.33, and then it's always minus, right?
If you distribute the x, you have 2x cubed, and then take the integral, it should be 2x.
Well, that's the top. I'm doing the bottom right now
Oh,
because
yeah,
I'm wimping
right.
out. I'm wimping out and doing the easy one first.
My bad, my bad.
No, that's not bad. Thank you for speaking up. That's what I want you to do. So I don't think see anything wrong with that. So that I feel a little weird. It's like I got a negative number. Wait a second. Like, that's not a negative force. Like, those are pushing down. What's going on here? I'm a little lost. Well, I'm gonna go back and put -1 in there now. And I got 13. Positive 13. So remember, integrals are always minus. So I'm actually going to get a negative answer for this. That's kind of bugging me. Is it bugging you? 106 2/3. But look at the picture. What direction are those forces going? They're going down. So actually, this should be negative.
So should we think about this as like I thought about it kind of like a moment, like they're going clockwise.
Mhm.
I guess it wouldn't matter.
Well, I haven't figured a moment yet, but it does, as far as moment around the origin, it looks like there's more force to the right. So it's like overall it wants to rotate right. It's kind of what it looks like. But remember, I've got A and B to reactions to stop it from doing that. But I'm actually back to being bothered again, because notice that 28, the 10, and the 18, those aren't negative. When I plugged numbers into that formula, I got positive 28 and positive 10. I got positive forces for that. So maybe although they're aiming down, they're positive. It's like this came out negative, and I actually can't see that I made a mistake. So I'm actually bothered by that.
I'll get a negative in the other equation and they'll cancel out.
Maybe the top equation will be negative and then it'll cancel out. That's hopeful. So then just to write it out, because I'm afraid I'm going to screw it up, then this would be, yes, 2x cubed minus 8x squared plus 18x. And then I would be taking the integral of that. So the integral of 2x cubed would be add 1 to it. So it'd become 2x to the 4th and then divide by 4. 8x squared would become 8x cubed. And then I'd be dividing by 3. And lastly, 18x squared divided by 2, then that'd be a 9x squared. And so that's got to get evaluated at 4 and -1. Say it again?
Yeah.
So you can't distribute the x first.
Yeah, I did. I did, because this was 2x squared, but then it's multiplied by x. So that's why I have it 2x cubed. And then I took the integral, and then it jumped to an x to the 4th.
Every time you type the integral, you can move around. With them. So it makes sense. You can turn the 2, the 3, and take something out of that and move to the prime. But it'll just get you to more fractions of it. That's a lot.
So if I didn't type this in wrong, for my first answer, I got 101 101 1/3. And then it's always minus, and I'm going to plug -1 in. And you do have to be careful putting -1 in, because if you do it in the wrong order, you get it wrong. I got 12.17 approximately, so I'm going to get a positive number up there. So that's not so good. I'm bothered by this extremely. I'm wondering if I made a mistake someplace.
Is this, oh, that's.
So x bar equals 89.17, if I haven't made a mistake. -106.67, which is approximately
I guess that could make sense. That's telling us our
I feel like something is wrong here.
magnitude is located at negative 0.83 meters.
Would you agree the magnitude of the resulting force was the negative 106.67? And since all of these weights were in pounds, that'd be pounds. So again, that bugs me because it should be positive. All these other ones up there were positive. I'm hoping I did this before and have a note. Something's wrong, I'm pretty sure. Yeah, I didn't get the same answer. We should have got 73 for this. What's wrong with that? The bottom one. Oh, I see one mistake. See that plus sign right there?
Oh, you subtracted.
I have a minus sign down here. So that was stupid. So that's good because this actually should come out as positive. I was right to be bothered by that. Those other numbers were positive, even though they were aiming down. So should our load. So something's wrong there. You guys should have caught me then. There's like 6 of you out there. You can't even copy a plus and minus sign, right, man? You guys suck, man. I need a new brain, man. I can't even copy stuff down right. As I say in a lot of my classes, though, I like to make those kind of mistakes in front of students. I mean, wouldn't be good if I couldn't do anything, but it's like that should put you at ease, right? I mean, if you did a problem like this on the test and you got that answer and reported it, at least I could just go circle those 2 and say, dude, and take 1 point off, right? If your work is clear. But remember, everybody still dies. You're an engineer, so it's like good that it was just a small mistake, but the whole crane still fell over. Broke into a million pieces.
You say that in court. You're like, listen.
Yeah. Listen, there's like 5 other people here, so why am I on the stand?
I just copied them.
In the interest of time, just because I'm looking at my old notes, I got 70. You can double check this if you want, but last time I did this, I got 73 1/3 for that. But I want to illustrate something. It's like, that's why it's important to kind of know what you're talking about. Because I was, right in front of you, I was being bothered by something. It's like, this doesn't feel right. And it wasn't because I've done it before. I knew the answer. It was just because I shouldn't have got a negative number there. And so. So I actually get like 1.22 for this. And this is a location, so that would be feet.
You have to do it on parentheses.
Yeah.
So how do you?
Maybe I'm sure.
So do you understand that the 73 was the magnitude of the resulting force? And doesn't that feel better? Because didn't we have 28s and 10s and 18s? Remember, those are per foot. So it's not like you have millions of other forces. It's like every foot is 28, but then it's changing. So at least the 73 sort of makes sense. Do you understand what the 1.22 represents here? Notice it's positive. Look at the XY axis. It basically means and we'll be done with this. It basically means if you went over 1.22 feet, since this distance is 2, wouldn't that be about here? That's where your 73.3 pounds would be located. So now we don't have a billion forces that are all defined by a crazy parabola. We got one, and we know where it's located. And so that might make wouldn't that make our sum of the moments around A and B to find the reactions? I notice this one isn't weird. It just means that A and B are each gonna get combined, have to handle the 73. So maybe one is 40 and one is 40, 33 or whatever. I mean, I could do this some of the moments now, and that'd be possible to do. It'd be easy to do now, right? And of course, that's the important thing. They aren't asking that, but that's the kind of thing you should see on a test. Okay, so let's get out of here. But my intention was to have you guys flip these over.
Yeah, you can do that. I'm
Oh,
fine.
yeah.
Yeah, fine.
In the bottom is
Glue the backside of these, but I think I'll just do it for you.
Well, it's basically yours.
And I'll bring them back with, you guys glue the top side,
Yeah.
I'll glue the back side, and then hopefully next class on Tuesday, we can actually glue it together, so it looks like this, and we'll let it set up, and then on Thursday, we just.
So
Yeah,
what's
use the
thoughts on
same
that?
amount of glue that I use.
I don't think there's not that much glue left in the bottle. So if you got any stuff for me, I emailed you guys this, but you should have the house rest and the boom project. And listen carefully here really quick. These homework questions are legit. They're hard. It's not as though like you watch me teach this and you should just go home and watch television while you're getting them done. Like you guys should be asking me more questions. Don't turn stuff in to the extent that you can, knowing it's wrong. You should be talking to me. You should need hints on stuff. That's totally part of this class. Lots of hard questions in those assignments. These two projects were hard. Check your project with me before you turn it in. Ask me questions. I did a Zoom with Tristan and Connor. It only took like 5-10 minutes, and it's like they didn't even have to come in here. Just send me an email or a text, and we'll just have a quick conversation about it. I can do it from home. So this is a hard class. Don't expect you should just be getting all the questions right. I usually don't remember, like maybe some of the questions I assigned are hard. It'd be kind of nice if I warned you about that. Sometimes there's one in there that's tough. And that boom project, as I said in the email, like, if you get that without a hint, you're a genius. Like that's ridiculously hard. You should need a hint on that. But you learn a lot from that. That's why I call them projects, because I want you to grow from them. But that doesn't mean I'm not kind of willing to give you a hint. So ask me more questions, I guess. All right, you got anything to give me? Give it to me.
And then are you gonna be going to your office right now? or-
Yep.
Okay, hold you which one, Doug? I got your number, dude.
I know. I gave it to you for a reason.
I'll send you all throughout the hours of the night.